Welcome to AI Paper Slop, where we're looking directly into a paper today called Variable Width Transformers by researchers from MIT and the MIT IBM Watson AI Lab.
Yeah, and they introduce an architecture they call the former, which is spelled with the greater than and less than signs, but pronounced the hourglass former.
Right, the hourglass former. And the headline finding here challenges this massive foundational assumption in AI, which is that transformer layers must maintain a uniform width from the first layer to the last.
Exactly. Instead of doing that, they keep the early and late layers wide, but they physically squeeze the middle layers into a computational bottleneck.
And by doing that, they manage to match the total parameter count of standard uniform baselines. But the kicker is, it cuts training FLOPs by up to 22% and reduces the KV cache memory and I/O costs by 15%.
Which is just a massive efficiency leap, honestly. And they do all of this without sacrificing any downstream performance.
Right. They're just reallocating the model's parameter budget instead of shrinking its overall capacity.
Yeah.
So for anyone tuning into AI Paper Slop, that stat alone immediately forces a question, right? Why hasn't this been the standard design all along?
Oh, I know. It seems almost bizarre that the entire industry just settled on uniform width.
I mean, is there some insurmountable hardware limitation we've been catering to? Or has uniform architecture simply been this massive blind spot?
Well, I mean, the field naturally gravitated toward uniform width, mostly just out of convenience.
Because it's easier to code.
Yeah, exactly. When you are writing model architectures in PyTorch or JAX, it's incredibly easy to define one standard transformer block and just, loop it 40 or 80 times.
You just copy-paste the layer and call it a day.
Right. It makes the math predictable, the code is highly modular, and most importantly, our entire hardware ecosystem is built to multiply uniform square or rectangular matrices.
But stepping back, there is no fundamental physical law of computation demanding that every single layer in a network requires the exact same parameter budget to do its job.
No, not at all.
Sure.
Different depths perform completely distinct semantic functions.
Okay, so let's figure out how they actually execute this physical squeeze mid-network. Because dynamically changing the dimension of a transformer layer sounds like a recipe for destroying the residual stream.
It really does. Because normally, if you have a wide output from, say, layer 4, you'd need a massive, computationally expensive projection matrix to shrink that data down to fit into a narrow layer 5.
And that learned projection matrix approach would introduce way too much overhead, right? It would just be unstable.
Oh, yeah, far too much overhead. But the paper bypasses that entirely. They introduce what they call a parameter-free residual resizing mechanism.
Wait, parameter-free? How does that work?
So the architecture actually maintains a fixed, global residual stream dimension from start to finish. The total pipe size never actually changes.
Okay, so the pipe stays wide, but what each specific layer is allowed to access changes based on its position in the network.
You nailed it. Each layer only reads from and writes to a very specific slice of that global stream. So when the architecture hits the bottleneck and narrows, the extra dimensions are simply truncated for that specific layer's computation. The layer just operates as if the network is small.
Let me try an analogy here. Think of this like a multi-lane highway where the middle lanes are completely closed off for construction.
Okay, I like that.
If you are a piece of data, like a specific dimension traveling in one of those closed middle lanes, you don't just disappear when you hit the bottleneck.
Right, you aren't forced into the slow lane.
Exactly. You just cruise straight past the construction zone entirely untouched. You completely bypass the localized computation until all the lanes open back up later in the network.
That's a perfect way to visualize it. And the paper refers to this as the carry forward method.
Carry forward, right?
Yeah, because when the network expands again after the bottleneck, the previously truncated coordinates are restored exactly as they were from the most recent layer that actively processed them.
And they tested this against other methods.
They did. The researchers ran extensive ablation studies on this specific mechanism. And the empirical results proved this carry-forward method significantly outperforms the alternatives.
Alternatives like what? Just zero padding?
Yeah, zero kiting the extra dimensions, or, like we mentioned earlier, trying to train a projection layer to predict what those dimensions should be.
Because training a projection layer just adds parameters that don't directly contribute to the actual language modeling task.
Precisely. And there's a mathematical guarantee built into this carry-forward design.
Which is?
Well, because a layer's parameters scale quadratically with its width, but the attention FLOPs and the KV cache scale linearly, manipulating the shape yields a definitive, measurable advantage.
The math is just very clear on this.
It really is. If you match the total parameter count of a uniform baseline, redistributing that budget into wider ends and a narrower middle guarantees that your variable width model will have a strictly lower average layer width.
And that reduction in average width is what actually drives down the attention, FLOPs.
Right.
And reducing the KV cache is just critical for inference.
Oh, absolutely critical.
Just to clarify the stakes there for anyone dealing with deployment, the KV cache is the stored memory of previous tokens, keys, and values.
Right, which is what allows a model to generate new text without constantly recalculating the entire sequence over and over.
So a 15% reduction in that memory footprint directly translates to being able to serve much larger batch sizes to users on the exact same GPU.
Which is huge.
Yeah.
It acts as an undeniable algorithmic win. You get the same parameter capacity for learning representations, but you execute fewer operations to utilize them.
Okay, so the ability to manipulate the width is established. Which brings us to the shape itself. Because the researchers didn't just guess that an hourglass would work best, did they?
No. They ran rigorous empirical sweeps at the 500 million parameter scale, testing multiple configurations.
What other shapes did they look at?
They look at the hourglass shape, a diamond shape, which is narrow at the ends and wide in the middle, a V shape that progressively grows, and a Kara shape that progressively narrows.
And the hourglass shape consistently outperformed the rest.
It did. The empirical data heavily favored the former across all those configurations.
See, I have to push back on those empirical results, though, because to me, they feel incredibly counterintuitive given the current literature.
How so?
Well, prior work, specifically those studies by Akita and colleagues focusing on feed-forward networks, suggests that the complex semantic processing, like the real heavy lifting of understanding language, happens in the middle layers of a model.
Right, the middle layers.
So logically, doesn't that imply we should be giving those middle layers more capacity? Like the diamond shape, not starving them of parameters. Why does squeezing the very layers responsible for semantic processing actually improve the architecture?
That's a great question. And the tension between that intuition and the empirical reality comes down to what you are actually resizing.
Okay, explain that.
So the prior findings regarding MLPs are accurate in isolation. But when you reallocate the full block width, meaning you shrink the attention heads, the residual dimensions, the MLPs, literally everything at once, the dynamics of how the network routes information fundamentally change.
It changes the whole routing system.
Exactly. The paper's sweeps showed unequivocally that the diamond shape performs worse under a full block reallocation.
Because it forces the model to adopt a totally different processing strategy.
Yes. And the optimal shape they landed on isn't even a perfectly symmetrical hourglass.
Wait, really? It's asymmetrical.
Far from symmetrical, yeah. The best recipe they found, and this holds true across multiple model scales, is a highly asymmetrical bottleneck.
Where is it positioned?
You place the narrowest layer at exactly 75% of the total depth, and you shrink its dimension down to 30% of the baseline width.
Oh, wow. So the network stays very wide for a long time, compresses sharply super late in the processing stage, and then opens back up right before generating the output token.
Exactly. That's the winning recipe.
And the results they achieved with that specific asymmetrical shape are pretty staggering. I mean, they scaled this up through dense models of 200 million, 500 million, 1 billion, and 2 billion parameters.
Yeah, and they even tested a 3 billion parameter mixture of experts model. The power law scaling curves mapped out in the paper are just incredibly tight.
So at the 2 billion parameter mark, how does it compare?
The 2 billion parameter former achieves the exact same language modeling loss as the uniform 2 billion baseline, but it does that using only 77.8% of the FLOPs and 85.1% of the average layer width.
That amounts to a massive compute discount for the exact same predictive capability.
Massive. And it goes beyond just pre-training loss, too.
Right. The former consistently wins on perplexity tasks, and it completely dominates natural language understanding benchmarks.
Yeah, tasks like ARC, HelloSwag, and Winogrande Grande at that 2 billion scale.
But looking at the scaling curves in the paper, it reveals a detail that I think is even more critical than the sheer performance numbers.
The exponent, right.
Exactly. The former doesn't just have a smaller intercept on the graph, meaning it starts off more efficient. It actually has a slightly steeper scaling exponent.
Which means the gap between the uniform model and the former actually widens as you inject more compute into the system.
So the larger the model gets, the more pronounced the efficiency gains become.
Precisely.
I mean, that steeper exponent changes the conversation entirely.
Mm.
If that scaling trajectory holds as we move toward frontier models with 100 billion or like a trillion parameters, abandoning uniform width isn't just a neat architectural trick anymore.
It becomes an economic necessity.
Yeah, the compute and memory savings at that scale could honestly dictate whether a model is commercially viable to serve or just completely cost prohibitive.
Absolutely. Because doing less work to achieve higher performance means something fundamental is shifting inside the network's processing pipeline.
So to understand why this hourglass shape is so efficient, we really have to look at the internal mechanistic interpretability of the model.
We do. We have to ask, what is actually happening to the token representations inside that physical bottleneck?
Right. What's going on in there?
Well, the paper points to a phenomenon known as compression valleys.
Compression valleys.
Yeah. Recent interpretability work has shown that in standard uniform language models, the middle layers often suffer from severe representation collapse.
So the model is provided with this massive parameter budget, and it basically just gets lazy.
It gets incredibly lazy, and we can actually measure that laziness mathematically.
Don't you measure it?
If you track the normalized matrix entropy of the residual stream.
Which is basically a metric of how evenly the model is spreading its information across all its available hidden dimensions, right?
Exactly. That entropy drops to near zero in the middle layers of a standard model.
Near zero.
Yeah. The network is taking rich, high-dimensional token data and just projecting it into a highly degenerate, low-rank subspace.
Meaning it is barely utilizing the massive width that the engineers paid millions of dollars in compute to provide.
Right. It's a huge waste.
We can view this almost as a computational version of Parkinson's law, right? You know, the adage that work expands to fill the time available for its completion.
Oh, that's a brilliant way to frame it.
Here, if you give a model a massive uniform width across 40 layers, data expands to fill the space available, but in a highly inefficient way.
Yeah, it relies on a few massive outlier dimensions to carry the signal and lets the rest of the capacity effectively just die.
But by physically squeezing the width in the former, you are introducing a structural regularizer.
Exactly. The bottleneck forces the model to pack information densely and actually utilize every available dimension.
It has no choice but to be efficient.
Right. And the paper quantifies this structural regularization by plotting the energy participation ratio, or PR.
And the PR measures how evenly the computational energy is distributed across the model's dimensions.
Yes. In the baseline uniform model, the effective width completely collapses. The PR drops to less than 5% of its capacity by layer 10.
Less than 5%. So 95% of the dimensions in those middle layers are functionally dead weight.
Complete dead weight. But the former avoids that trap entirely.
How does its PR look?
It maintains a dense, evenly distributed activation profile amounting to roughly 1,000 effective dimensions, straight through that middle section where the baseline model experiences representation collapse.
So the bottleneck prevents the collapse by physically restricting the available space, forcing the network into a high entropy state.
Exactly.
And we can actually observe the tangible effect this dense packing has on the model's predictive dynamics, right? Using a technique called the Logit lens.
Yes, the Logit lens analysis here is fascinating.
For anyone who might need a brief refresher, the Logit lens is an interpretability tool where you take the hidden states from the middle of the network and multiply them by the final unembedding matrix.
Right, which projects those intermediate representations directly into the vocabulary space.
Letting us peek at what token the model is leaning toward at that exact layer, long before it reaches the very end of the network.
Exactly. And applying the Logit lens to the former yields striking results. The former assigns higher probabilities to the correct target token much earlier in the network compared to the uniform baseline.
It just solves the prediction problem sooner.
It really does.
And once it locks onto that prediction, its internal states seem much more stable.
Yeah, we see that stability when measuring the layer-to-layer KL divergence.
KL divergence, right. That tracks the statistical distance between two probability distributions.
Correct. In this context, it measures how wildly the model's token predictions swing from one layer to the next.
And the former is more stable.
Much more. The former exhibits a remarkably stable and smooth distribution through its middle layers.
While the uniform baseline, burdened with all that unused, unstructured space, exhibits highly erratic changes.
Exactly. Intermediate representations are essentially just thrashing around in those lazy middle layers.
The baseline just has too much room to wander, whereas the former is tightly constrained, moving purposefully and efficiently toward the final prediction.
That's exactly what's happening.
Okay, so we have a mathematically sound, empirically verified architecture that acts as a structural regularizer, prevents dimension collapse, and cuts FLOPs by 22%.
It's incredible.
It really paints this utopian picture of AI efficiency. But we need to ground this in reality for a second.
Uh-oh. Here comes the catch.
Yeah. If this architecture is a strict upgrade, what is actually preventing major labs from deploying it in their frontier training runs today?
Well, the friction lies entirely in the current state of our hardware and infrastructure stack.
The hardware just isn't ready for it.
No. Modern GPUs, alongside the standard tensor and pipeline parallelism techniques we use to train massive models, are obsessively optimized for uniform matrix shapes.
The entire software ecosystem assumes every transformer block is a neat, identical square.
Right. Let's look at tensor parallelism, for example. This is the technique of splitting a massive matrix multiplication across multiple GPUs to share the memory load.
Standard practice for large models.
Exactly. But if your matrix shape keeps changing from layer to layer, specifically shrinking to 30% of its size in the bottleneck, you can't distribute those computations evenly.
You end up with severe load balancing issues.
Yep, some GPUs finish early and just sit completely idle, waiting for the others to catch up.
And pipeline parallelism faces a similar nightmare, right? If layer 1 takes 10 milliseconds to process, but layer 20 only takes 3 milliseconds because it's in the bottleneck, the sequential flow of data creates massive pipeline bubbles.
Huge bubbles. And the parameter-free residual resizing mechanism actually exacerbates this at the systems level.
The carry-forward method. But you said it was elegant.
The carry-forward method on our multi-lane highway is incredibly elegant on paper. But from a systems engineering perspective, slicing, copying, and zero padding, the global residual stream requires extra kernel launches.
Oh, and a GPU kernel is essentially a tiny, highly optimized program that tells the hardware exactly how to execute an operation.
Right, and standard kernels are built for uniform memory blocks. Executing awkward, heterogeneous copy commands forces the GPU to use unoptimized memory pathways.
So let me get this straight. While the architecture theoretically saves 22% of the FLOPs, the actual wall clock time spent training the model might currently be slower.
Unfortunately, yes. Because the GPU is bogged down executing inefficient copy commands and waiting on idle processors.
It creates a massive standoff. Heterogeneous per-layer whiffs generate so much friction with existing tooling.
They really do. The AI labs have to decide if a 15% reduction in KV cache and a 22% drop in theoretical compute is worth the massive engineering investment required to write highly custom fused kernels to make this architecture actually run efficiently on, say, an H100 cluster.
But it highlights that the limitation isn't algorithmic, it is purely a tooling constraint.
Entirely tooling.
And historically, when there's a 20% efficiency gain sitting on the table, the engineering infrastructure eventually evolved to capture it.
Oh, absolutely. Purpose-built kernels for variable width architectures will inevitably be written. It's just a matter of time.
And that points to a real paradigm shift in how we conceptualize neural networks. This paper demonstrates that a fixed parameter budget should not be spread evenly like peanut butter across a network.
No, it shouldn't. We have spent years building computational skyscrapers where every single floor has the exact same square footage and layout.
Completely ignoring the reality that the lobby, the maintenance floors, and the penthouse serve entirely different functions and require different capacities.
Exactly. We must begin treating depth and capacity allocation as dynamic variables to be optimized, rather than just fixed constants dictated by PyTorch defaults.
Which leaves a fascinating concept for you to explore as you apply these insights to your own work.
What's that?
Well, if physically squeezing the width of a transformer acts as a vital structural regularizer to prevent dimension collapse, what other uniform hyperparameters are currently making our models lazy?
Oh, that's a great question.
Consider the uniform processing of sequence length across every single layer, or the uniform depth and dimension of attention heads regardless of their position in the network.
Right. Do they all need to be the same?
Exactly. If our multi-lane highway doesn't need every lane open at all times to reach the destination, what other structural bottlenecks are just waiting to be engineered to optimize how these models actually process information?